Good afternoon, everyone. Thank you for being here. My name is Dorothy Hanna, and I am the Program Administrator for the CAXT MIT Ibn Khaldun Fellowship for Saudi Arabian Women. Welcome to today's IDK webinar presented by Dr. Fatima Adhaim based on her research at MIT this year, which is titled Mixed Matrix Membranes Formed from Different Morphologies of Zeolitic Amidolate Frameworks for Gas Separation. Please post your questions in the chat as we go along, and we will answer them at the end. And first, our program director, Professor Kamal Yusuf Toumi, will introduce Dr. Fatima's advisor, Professor Zach Smith.
Great, yeah, thank you. Thank you, Dorothy, and thank you for everyone for joining us this afternoon. This is part of the Ibn Khaldun Fellowship Seminar series. I would like to thank Professor Zachary Smith for working with Fatima and supervising her activities in his department. So Professor Smith is a professor at the Department of Chemical Engineering at MIT. His research focuses on the molecular level design and synthesis, and also the characterizations of polymers and inorganic materials. Some of the applications that he has been focusing on with his team is in the membrane and adsorption-based separations. And so Professor Smith, because of all of his contributions, has been recognized, with several awards. I'm just going to mention a couple of them here. One is the Early Career Award from the Department of Energy, the DOE, and also the Young Investigator Award from ONR, or the Office of Naval Research. And then in addition to that, he was recognized by the American Institute of Chemical Engineers in the program of the 35 Under 35 Award. He has published extensively in these areas, and he also co-founded the Flux Technology and Osmosis Incorporated company. Professor Smith has earned his degrees in chemical engineering from Penn State University, and also his master's degree, his PhD from Texas Austin. He has done also a postdoc in the past at the University of California, Berkeley. So thanks again, Zach, for all your help with not only with Fatima, but also with our Ibn Khaldun program. And maybe I'll hand it over to you, maybe to have an introduction of Fatima before her presentation. Thank you.
All right, well, thank you, Kamal, for the introduction. I'm really happy to introduce Fatima as well. I'm excited for the presentation today. Fatima comes from, of course, Saudi Arabia as part of her fellowship, and she's trained in chemistry, actually completing her chemistry degree back in 2004 at the Girls College in Dammam. She went on to work at Saudi Aramco while also pursuing degrees at KAUST, and this includes her work with her MS and also her PhD. And where Fatima really stands out is working in the realm of inorganic materials, crystallography, characterization type work. And so when she came to my lab at MIT, I of course put her on a really hard project that involved inorganic chemistry and characterization. She came around 2019, 2020, so just in time for the pandemic, actually, but dove right into the lab making things and adjusted very well during the time where we were away from campus, and then eventually getting back to shift hours, and just recently back to what is a semi-normal routine and actually having in-person meetings. So she's been here that entire time and has done a wonderful job working with ZIF materials that she'll talk about today. Also came here with her family, who I had a chance to meet as well just recently. So I had to balance lots of things during this time, but really appreciated all the work that Fatima did, and really excited to see this final presentation on her work. So Fatima, when you're ready, you can go ahead and get started. We're looking forward to your presentation.
Thank you, Professor Zach, for the nice introduction and the kind words. Just a moment. So good afternoon, everyone. Today I'm going to explain and show some information related to my work at MIT entitled Mixed Matrix Membrane Formed from Different Morphologies of Zeolitic Imidazolate Frameworks for Gas Separation. During the presentation, I'm going to give you a brief introduction. Then I'm going to discuss the synthetic factor controlling the particle size and morphologies of ZIF8. After that, I'm going to talk about the structural effect of MOFs on gas permeation via mixed matrix membrane. And finally, I'm going to conclude the presentation with a conclusion and acknowledgements. So let's move into the first part of the presentation, which is the introduction. In fact, the natural gas consumption steadily increases every year, as do CO2 emission. In 2016, the total US energy consumption was around 98 watts out of 4 different sectors. Chemical and petrochemical industries consume around 32% of this energy. However, half of this energy is consumed by the thermal separation, like distillation, drying, and evaporation. However, the most energy is consumed by the distillation process. It has been confirmed that the membrane material would save around 90% of this energy comparing to the distillation process. So implementing more energy efficient separation method would reduce the greenhouse gas emission and save a lot of money. Membrane material can be used as an alternative to the conventional separation method, not only because membrane material consumed lower energy comparing to the others, but membrane material could increase the separation efficiency up to 90%. Comparing to the solvent system, membrane system would require smaller spaces. Furthermore, membrane material can separate both organic and inorganic substances. Membrane materials are clean technology with operational aids as well. However, the most of the commercial membranes that are available in the market are made by the polymers, and the polymeric membrane are associated with some drawback, like the upper bound trade-off and the permeability and the selectivity. Furthermore, there is an issue or challenge in this material in terms of the stability against the blastization. I mean by that, at higher pressure, this material would start to swell the CO2 and the hydrocarbons, and in this case, it would result in higher permeability, and the higher permeability of the polymeric membrane are usually associated with a significant reduction in the selectivity. So on the other hand, a pure MOF membrane can surpass this upper bound. However, this material becomes so fragile in case if we scale up this material into industrial scale, which would result in poor film formation. In a pure sense, mixing these two components and the advantages of the polymer and component would result in a mixed matrix membrane with good processability, high performance, and resistance to the plasticization. However, there is a wide range of MOF material, and the gas separation and gas transport of mixed matrix membrane depend on the type of MOF that used in it. So I was working on the zeolitic imidazolate framework. These material are a subclass of metal organic framework. These material inherited the tunable porosity, structural flexibilities, and the functionalization of the internal surface of MOF material, as well as they inherit the thermal, mechanical, and chemical stabilities of zeolite material. These material possess interesting properties owing to their structure. So the basic repeated unit of zeolite material, silicon oxygen silicon, is represented in ZIF material with a transition metal in place of silicon atom and imidazole in place of the bridging oxygen atom. Also, the angle that made by the transition metal, imidazole transition metal, is similar to that in zeolite material. ZIF8 material was a sodalite structure with a small aperture size of 0.34 nanometer and large cage of 1.16 nanometer. However, the gas transportation of ZIF material depends on the particle size and morphologies. Therefore, I was working on this material with an ultimate goal of being able to systematically tune the size and morphologies of ZIF8 and then study the gas transport. So in order to achieve the first part of my goal, I have to answer several research questions. like what is the effect of the modulator addition, what is the influence of the reaction time and temperature, the influence of zinc sources and molar ratio, and what is the influence of solvent that is used in the reaction. And the most important question is that, would it be possible to generalize our method into other ZIFs like ZIF 67? So in order to answer all of these questions, we need to know that ZIF 8 material can be constructed from any zinc precursors plus 2-methyl-imidazole. Methyl-imidazole can work as a stabilizer in its natural form and as a linker in its deprotonation form. Furthermore, the low pH can lead to stabilize the linker in its natural form. Looking into the stoichiometric equation, we can see that as ZIF material is formed, nitric acid is also formed, and this would lead to decrease the pH of the solution, which would limit the rate of the phase transformation. So the main reason to add the modulator in this case is to enhance the reaction by deprotonation of the ligand and denucleation of the material. So the deprotonation modulator would maintain the proper protonation state. Furthermore, it would neutralize the acidic product. However, in order to study the synthetic factor controlling the particle size and morphologies of ZIF 8, we need to answer all of these questions and investigate all of these reaction conditions. However, due to the time limit today, I'm going to show you only the effect of the modulator addition, the influence of the reaction time, the influence of zinc sources, and would it be possible to generalize this method into other ZIFs. So in order to start with the effect of the modulator, I've used 10 amine-based modulator and 8 different zinc sources. But today I'm going to show you the result related to zinc nitrate hexahydrate. The reaction was held for around 60 minutes at room temperature using methanol as the solvent. So TM result shows that in case of the absence of the modulator, ZIF material possesses large particle size with rhombic dodecahedral shape and sharp edges and corners. However, in case of the addition of pyridine as a modulator with low pKa value of the conjugated acid, we can see that there is a slight reduction in terms of the particle size. And also this particle possesses irregular morphology, and we can see there is no sharp edges or corner in this case. Addition of aniline, which was a slightly higher of pKa value, we can see that the particle size is getting smaller and they are still attaching into each other. However, the addition of trimethylamine with higher pKa value, we got the first branch material. And as you can see here, the particle is much smaller than the others, and the morphology in this case, the particle like nanostrand attaching to each other in random direction. Further, smaller particle size can be obtained from the higher pKa in butylamine, and in this case we can see that the particle size is much smaller, and this behavior actually can be attributed to that the addition of the modulator would enhance the nucleation of the ligand and hence rapidly nucleate the ZIF 8 material. And this nucleation of ZIF 8 material, I mean the particles out of this rapid reaction would grow into smaller particle size because there is no time for these particles to grow up due to the rapid reduction in the supersaturation solution. So as these reactions have been repeated several times using 8 different zinc sources and different 10 amine-based modulator, and we usually get the same trend, we can confirm that deprotonation by the ligand, the deprotonation of the ligand by the modulator would affect the morphology of ZIF 8. Furthermore, the modulator with higher pKa value can rapidly deprotonate the ligand, which would lead to rapid enucleation and small particle size of ZIF 8 material. The influence of the reaction time has been also investigated using 5 different modulators, and today I'm going to show you the results related to triethylamine with zinc nitrate hexahydrate. The reaction time was 5, 10, 13, and 16 minutes. The X-ray diffraction of this result confirmed that the intensity of the prominent peak increases as the reaction time increases as well, and this indicates that the material or longer reaction time would lead or result in larger particle size. However, the presence of sharp peaks, even for the reaction that have been done in 5 minutes, confirm that these materials can be successfully synthesized in a short period of time. Furthermore, to confirm the absence of the presence of zinc oxide as impurity or byproduct of this material, the peaks between the area between the peaks in this area between 30 and 42 theta degree have been matched with the reflection from the resulting material. And as you can see here, the peaks belong to the simulated zinc oxide are not matching the peaks from the resulting material, confirming the absence of this material. However, all of the reflections that are obtained from the simulated ZIF material are perfectly matching the peaks or reflections that are obtained from the resulting material, confirming the purity of the material and confirming that the material are pure ZIF-8. TM results also confirm that all of these material are branch material, even the material that synthesize at shorter time of 5 minutes. And as you can see here, as we go from 5 minutes to 60 minutes, the particle size getting larger and larger. And by this, we confirm that the longer reaction time would lead to larger particle size, and the branch material can successfully synthesize in a short time of 5 minutes. The influence of zinc sources has been also studied. So in this case, I use 6 different reactive zinc sources, but today I'm going to show you the result out of 3 zinc sources, which are zinc iodide, zinc bromide, and zinc nitrate hexahydrate, obtained from trimethylamine or from N-butylamine. As you can see here, as we go from the least reactive zinc source, which is zinc iodide, into the larger or higher reactive zinc source of zinc nitrate hexahydrate, the particle size getting smaller, and also we can see the differences between the and the morphology, I mean. So this can be attributed to that. In case of zinc nitrate hexahydrate, the amount of zinc ions that are available for the reaction is huge, which would lead to large amount of nuclei, and these nuclei can only grow up into smaller particle size because of the rapid reduction in the supersaturation solution. So as these reactions have been repeated also with different zinc sources, we confirm that the reactivity of zinc precursors can direct the assembly of ZIF-8 nanocrystals. And as you can see here, we observe that there is a reverse relationship between the particle size of ZIF-8 material and the reactivity of zinc sources. Furthermore, to confirm that our method would work with other ZIFs, I tried this method, I mean the addition of the modulator with other ZIF material. So I have tried it with ZIF 67 by using the same synthetic condition, and instead of using zinc nitrate, I use cobalt nitrate hexahydrate to obtain this material. And the result confirming that using 5 different modulators would result in a branch material, confirming that our synthesis procedure could work with other ZIF material. However, the main differences between ZIF 67 and ZIF 8 is the particle size. While the ZIF 67 possesses the larger particle size, the ZIF 8 possesses the smaller particle size. Furthermore, the PET surface area of this material confirmed that the presence of microporous material and mesoporous material due to the presence of a combination isotherm type 1 and type 4 as well, which confirmed the presence of both, the microporous material and mesoporous material. The X-ray diffraction confirmed the phase purity of this material and confirmed that this material is pure ZIF67. And whatever a question that I have for ZIF8, I had it here and I tried different synthetic condition, and more or less I got the same trend or the similar result out of ZIF67 and ZIF8. So by this, I kind of answering the inquiries that I have, and it is the time to study the structural effect of MOF material on gas permeation via mixed matrix membrane. The typical or basic polymer that I've used in this regard is 6FD Edhaim. I use this polymer because this polymer possesses thermal and chemical stability and showed good gas separation performance. And I have chosen 3 different morphologies. First morphology is ZIF, is rhombic dodecahedral with larger particle size that can constructed from zinc nitrate hexahydrate without the addition of any modulator. I also chose rhombic dodecahedral particle size with the smaller particle size, that are constructed from zinc bromide with a trimethylamine. The branch material that I chose is constructed from zinc nitrate hexahydrate with a trimethylamine. As you can see here, all of these materials possess very different morphologies. They possess the similar lattice structure of ZIF8 material. The main differences of this material is the intensity and the broadening of the peak, and these could be related to the particle size of the material. Furthermore, the BET surface area are comparable except for branch material. As we can see here, there is a combination of the isotherm type 1 and type 4 characteristic for micro and mesoporous material. So incorporating these particles with the polymer would result in different mixed matrix membrane, while the branch material can form transparent with no color film. The other materials, the RDZ material, either with a smaller particle size or larger particle size, would show more opaque, either white or yellowish color membrane material. The intensity, the thickness also of these membranes also increases as the particle size increases from the smaller branch material particle size to the larger rhombic dodecahedral size. Furthermore, in order to see how these morphologies distributed inside this membrane, the cross-section SCM took place. So for the rhombic dodecahedral with larger particle size, we can see ZIF material settling nicely within the polymeric matrix. However, in case of the RDZ with a smaller particle size, we can see here the agglomeration of the smaller particles of this material. And the morphology here is like a grape structure or morphology. For the branch material, we can't really distinguish between the ZIF material and polymeric matrix, which indicate a good adhesion of MOF material or of this filler in the polymeric matrix. A cross-section focus ion beam also shows that a wide size distribution between 30 nanometer to 300 nanometer obtained from RDZ with larger or smaller particle size, and this can be attributed to the agglomeration of these particles. However, in case of branch material, we can see uniform dispersion across the entire film. And the blastization resistance of ZIF8 of these morphologies have been studied as well. And as you can see here, this is the typical blastization curve for the polymer itself. And as you can see here at the beginning or initially, there is the probability decreases up to 200 BSI due to the sorption mode. And then the probability significantly increases. And this this actually unwanted behavior of the polymers, because this behavior indicates that the polymers start to swell the CO2 gas, which would negatively affect its performance in the real application. However, incorporation of the RDZ with either larger or smaller particle size, we can see some reduction of this behavior. More incorporation of these material would be to disappear the upturn curve, which indicate that the incorporation of the RDZ either with larger or smaller particle size and with high MOF loading would result in, would increase the blastization resistance. However, in case of the branch material, incorporation even of small amount of this material would result in the absence of this upturn curve, indicating that the branch material would significantly increases the blastization resistance. Furthermore, the selectivity of this material of hydrogen over nitrogen also enhanced for ZIF material, for RDZ with the larger particle size comparing to the pure polymer. So the selectivity here and permeability increases as we are increase the MOF loading. However, for the RDZ with smaller particle size, we can see that there is enhancement of the selectivity of hydrogen over the nitrogen, while the permeability, especially for 30 and 40 weight percentage of MOF loading, be the same. The selectivity and the permeability of branch material with smaller particle size, however, enhanced, and this can be attributed to that the branch material can form something like a percolation network comparing to the larger particle size. So these larger particle size cannot be attached to each other to form this kind of these channel as well. So I have obtained the same trend for the selectivity of the hydrogen over methane as well. And by this, we confirm that the BZ material would show great gas separation performance comparing to RDZ with either smaller or larger particle size. So in this case, I would like to conclude this part of the presentation by that synthetic condition would play a significant role in controlling the size and morphology of ZIF-8 material. And in order to obtain smaller particle size and enhance the gas separation, you can either use a modulator with higher pKa value, shorter reaction time, and more reactive zinc source. We also see the differences between the RDZ with larger or smaller particle size and the branch material. And we have been seeing that the branch material would show uniform dispersion across the entire film, and it would increase the permeability and selectivity as well as the resistance to the CO2 blastization. Beside the research work, I have completed several executive management and leadership programs from Sloan School, and I have obtained the certificate in strategy and innovation. I've also completed several courses in different areas, as well as I tried to enhance my leadership, communication, and mentoring skills by attending different webinar series. I have been trained also on several advanced analytic techniques in order to characterize my samples, not only here at MIT, but also at Saudi Aramco. And I have attended a course, and we are about to publish a manuscript with the other team. So at the end, I would like to thank Professor Smith for accepting me to work under his supervision. And actually, I would like to thank him for his advice and support, especially during the pandemic period. And actually, I feel that I'm lucky to work under his supervision and under this, in such healthy environment in his lab. I also want to thank everybody in the group here for making my journey at MIT more enjoyable. I also want to thank the IBK and the CACs, because without you, I won't be here today. A special thank also to Saudi Aramco, Aramco Americas, and MIT Energy Initiative. Thank you.
Thank you so much, Fatima, for that excellent presentation. It's certainly been a pleasure on the IBK side getting to know you this past year and a half. So it's great to hear all about your work. And I'm going to open the floor for questions. Please feel free to unmute and ask a question, or put a question in the chat, and we'll go from there. Kamal, please go ahead.
Yeah, thank you, Dorothy. And thank you, Fatima, for the great presentation. I learned a lot in all of these presentations, and definitely in yours, I have learned many things. You know, this is outside my area, but I have 3 questions, if it's okay, Dorothy and Fatima. So one is on the modulator that you talked about. Second one was the reaction time. And the third one will be on the scale up and perhaps the cost in comparison to others. So the first one is on the modulator. I think your results, show very clearly about the the influence, the effect of the modulator as you use it. Yes, exactly. In this slide, and you show how the size of the particles, end up being smaller. Not only the size, but it looks like also the shape, has been affected. So in the end, for the permeability, function of this material, I just want to understand. So as you clearly stated it, that the size, plays a role, the shape plays a role, and then in the end, the uniformity, like how uniform this configuration is. What is the role of that, and how, and if the uniformity in the sizes and the spaces between these particles, that have to be a certain way, what is in there that maybe allows this to happen in that way, or you have to do some additional tweaking to it?
Okay, so the permeability, as you can, as I've showed you, increases as the material being branched, comparing to the single crystals. So in this case, the branch material make something like channel, and we call it a percolation network. And this would enhance the permeability of the gases. However, in case of the particle size or uniformity of the particle size, as you can see here, for example, there is a range of the particle size. However, all of these particles are able to form this kind of channel, comparing to this material, which form a uniform particle shape. And actually, because these particles are apart from each other, they are not able to form this kind of connection, and hence this would affect the permeability of the material. So the uniformity in this case won't play the significant role, but the connectivity of the particle itself would have this role, or would control the permeability of the material. And as I have showed you, as we increase the MOF loading, the permeability become more and would increase. And this also because more connections would be appeared or would be available in this case, and more network can be obtained by increasing the amount, the MOF loading, I mean. So as we increase the MOF loading, the permeability, we are forming more networking, more more percolation network, and we increase the permeability.
Great, yeah. Thank you. The other question had to do with the reaction time, and if I understood correctly, I think you mentioned that if the reaction time is longer, and in your experiments you had from 5 to 10 to 30 to 60 minutes, that the size also became smaller. Yeah, and I wanted to understand your plotting intensity versus degrees, and I didn't understand what is it, an angle or something?
Okay.
It was in degrees. So basically just the graph.
Mm-hmm.
And then the other thing is that the matching or the mismatching, of the peaks,
Mm-hmm.
of these curves. One thing you mentioned, I think, in your presentation was about the purity of the material that was part in this graphs. And if you can maybe
Mm-hmm.
just elaborate a little bit on that, that I
Okay.
missed. Yeah.
So usually from the X-ray diffraction, if you have a nanoparticle and small particle, we usually have broadening in the peak itself. So the broadening of the peak would indicate the presence of two things, either amorphous material or nanoparticles size of the material. And here, for the reaction, the reaction that lasted in 60 minutes, we can see the green peak here, the intensity and the sharpness of the green peak is much higher, for example, than the material that synthesized for 5 minutes. So the black, if we compare the black curve here, in terms of the broadening and the intensity, we can see that the material that synthesized for 60 minutes possesses stronger and sharper peak, which indicate that the material is getting larger. However, as I have mentioned, the broadening of the peak indicating that the material is getting smaller, and this is what we've got here. And definitely these material are not amorphous material, because even for shorter reaction time, we can see these peaks are matching with the simulated pattern of the ZIF-8 material. On the other case, you are asking about the purity of this material. Yes, for the material synthesized for 60 and 30 minutes, we see these peaks are sharp. And in this case, I was wondering whether there is impurity and that lead to presence of these sharp peaks in this case or not. So I was wondering if zinc oxide is presented within the framework of the material or not. And as you can see here, when I try to match the peaks from zinc oxide, it is not matching at all with the reflections from the resulting material, which indicate the absence of this impurity.
Yeah, thank you, Fatima. I was just looking also at my notes, and I saw
Yeah.
the scribble that I made while you was talking. This was on slide 14, if you don't mind. And I'm asking because I wanted to understand. So
Yeah.
yeah, so these graphs that you have, the quantity absorbed on the vertical axis, and then the real axis you have the relative pressure. So, and it looks like there are different behaviors. So, like for example, in the middle graph, you have like the high absorption, very quick, right? Or very quick meaning like at even like a slightly lower relative pressures, and then it kind of levels off. So that is one. And then on the graph above it, it has like the same behavior, but when you start reaching like about one in the relative pressure, then it starts going up, right?
Yeah. Okay.
And then the bottom plot has also kind of the same feature or the same look, in a sense that it goes up at a, very quickly, or with a lower relative pressure, and then the slopes seem to be approximately the same. And then when you reach about 0.7 or so, So at that time, there's like it looks like another behavior is happening. So this attracted my attention,
Okay.
and so if you can maybe just explain, what is happening, that is making these at least to me, it looks like some interesting behaviors. Yeah.
Okay, so for this, this type of the isotherm, the typical isotherm for the microporous material, it should be like this one. Just a moment. Give me a moment. Okay, the behavior, the typical isotherm of the microporous material should be isotherm type 1, and it should be like this. However, the presence of this increasing or this behavior, that indicate the material possesses ultra microporous material plus the microporous material. So, for example, the microporous material should be less than 2 nanometer. However, the ultraporous material is the material that possesses a smaller particle size up to 0.7 nanometer. So the microporous material indicate a smaller pore size inside it, and this would lead to this kind of the behavior. However, for the mesoporous material, usually possess this hysteresis loop. So before that, I would say we have here the same behavior of the isotherm type 1, which indicate the presence of microporous material. However, the presence of this behavior, and we call it the hysteresis loop, this indicates the presence of larger particles, a larger pore size, and it is the mesoporous material, which is larger than 2 nanometer up to 15 nanometer. And from the shape of the particle size of the hysteresis loop, we can predict the shape of the pore itself, and this is type 1 cylindric pore shape. So this is
this is interesting when you mentioned like a hysteresis loop. So so this means that the test was done like in 2 different directions. Is that correct?
No, we use the same parameter has been, the same conditions has been used for all of these 3 materials, but the behavior of the material, the non-particles, the presence of mesoporous material here within the branch ZIF material that indicate these materials. Actually, the pores here is like interconnected pores because of the agglomeration of the smaller particles, and this would lead to this kind of behavior. So the same condition have been applied for all of these material, but if the material consists of only microporous, it would give this kind of the isotherm. However, if there is ultra microporous, we will get this type of the isotherm, which is it is the same isotherm type 1 for microporous materials. And if we have both, we're gonna get a combination isotherm.
Yeah. So I don't know whether this applies or not, but in our case, from the mechanical engineering point of view, for processes or behaviors that show something that looks like a hysteresis or hysteretic effect that you mentioned. So in that case, in that process, that means there are at least two things happening. One is the storage of energy, potential energy, with things that are like maybe some kind of elastic behavior or the equivalent of that. And then the other one is the dissipation of loss of energy, and the bigger the loop in the what looks like a hysteresis behavior, that means you have more losses there. Like you have an energy that is being applied into this system, or power that is injected, and then there's more dissipation, so the loops become bigger. So when the loops are smaller, so you have less dissipation, but in the end, you would have to have at least one behavior or phenomena that is storing the potential energy, the equivalent of that, and then the other one is the dissipation of energy, and those two have to be present, together to show or describe this hysteretic behavior. And then for systems that are purely elastic, then you will see only like one curve that has no loops in it, and then your graph, you're plotting like in the end some kind of a pressure versus the quantity absorbed, which is yeah. So in any way, so when we look at these variables from that point of view, so we have this kind of. So anyway, this is what came to my mind when you were describing. Whether it is related or maybe completely incorrect what I'm saying, but for what is happening in your membranes, but at least from the behavior of hysteresis or hysteretic behavior, what I mentioned is correct. Yeah.
Yeah. Actually, in my case. I usually get this type of the isotherm, I mean type 1 and 4, when I going from the single crystal or rhombic dodecahedral to branch material. So most of the branch material show this behavior.
Yes,
which indicate that most of the branch material, or actually all of them, possess both morphology both pores, micro and meso.
Yeah.
Mm-hmm.
So anyway, so this is so the other thing that when I look at plots like this, what comes to my mind is maybe more than one domain, like more than one energy domain is active in these experiments. So so the relative pressure, is affecting, let's say, some kind of like the fluidic side, like the gas, in the end, can be thought of as a fluid. Um, so that is like one domain. Then the other domain is that the particles themselves, maybe looking at the material perhaps in some kind of an elastic membrane. But anyway, I'm sorry that things are going in my mind in all these different directions. So, but thank you. Just one last question, Fatima. So I think in the end, this is the great, for of course, for using it in, I'm sure, many other applications, but definitely for the separation, gas separation. So what are the thoughts of maybe of the team, in Zach's group, about the scale up, and the cost associated with that in comparison, with these other methods, that you have mentioned at the beginning of your presentations. I'm sure that this method that you guys are using and developing, has advantages, also in that respect.
So what's the big question again?
So I'm assuming that the experiments and all that are being done at this time maybe are in the lab, maybe at a smaller scale. But then, sometime in the near future, these will be maybe adapted or applied, to like large scale separation process and so on. And so I was curious about, like, when we go to that stage, and one compares, let's say the existing methods, or perhaps other competitive methods that are being developed or being used, and one looks at them from, this point of view of the scale up, and maybe the cost that may be associated with them. Just a general thing. I mean.
Yeah, I agree with you. Actually, we gave a shot in our lab to scale up this material in order to obtain larger amount. I mean, we usually synthesize this material in a small amount, and we gave the shot to synthesize this material in order to obtain at least half a gram. but we faced some issue of the scale up, and I think the team that I'm working with are working on this to develop a new method that can give us the same trend, but with more amount of the material.
Thank you, Fatima.
Thank you.
Thank you, great presentation. I learned a lot today. Yeah, thank you.
Thank you.
We have a couple more questions in the chat. Well, both some nice congratulations on the talk, Fatima. And first one is back a question about slide 14. Find your way there.
Okay.
Why are you using different precursors, ZnBr2 and ZnNO32 in slide 14?
Yeah, in order to see the differences or the effect of the particle size, I usually, usually without using any modulator, we get a rhombic dodecahedral or single crystals. But in case of zinc bromide, which is least reactive zinc source, and the trimethylamine, which possesses the smaller pKa value, give me also a branch, single crystals of rhombic dodecahedral, but the crystal in this case is smaller than the crystal that presented with the material or constructed from the material that synthesized without the modulator. However, the addition of the modulator, same modulator with trimethylamine with zinc nitrate, which is high reactive zinc source, would result in a branch material. That's why I prefer to compare between the large particle single crystal, smaller particle single crystal rhombic dodecahedral, and branch material in terms of the gas permeability and selectivity.
Thank you. Any other questions for Fatima? And I'm seeing lots of congratulations and good jobs, Fatima, pouring in through the chat. So very, very good work. Zach, would you like to add anything?
I think it's a really good overview on the work that Fatima did. I was just wondering from a very high level perspective, we got a couple minutes, maybe you could describe what surprised you most about making these materials. You looked at many, many variables. Which one gave you a result that you didn't anticipate when you first started?
Actually, I did the mixed matrix membrane with ZIF 67 as well. And when I made this material, I thought that I'm going to have higher selectivity and permeability out of this mixed matrix membrane, but and this is more or less similar to the already published work. And in my case, actually, I got the opposite. I see that the permeability of the ZIF 67 is higher than ZIF 8, but the selectivity is lower. And I'm still thinking about, I have to investigate more and see what is the reason behind this behavior.
Yeah, very good. It's the next step for another study to come. Yeah.
Well, I think we will wrap things up there. Thank you very much, everybody, for joining us today. Thank you, Fatima. Great job.